Okay, so today I'm going to start my session on further discussions on binomial distribution and the Poisson distribution. In my last class with section B, I discussed about the two special probability distributions, one of which is called binomial and another is called Poisson. Poisson distribution is a special case of binomial distribution. Under certain conditions, a binomial random variable tends to follow Poisson distribution. I discussed a problem, and there you are going to identify it by yourself. So the problem is 10 coins are thrown simultaneously okay, 10 coins are thrown simultaneously. Find the probability of getting at least 7 heads, of getting at least 7 heads. Now, usually when we are given this type of problem, what we actually do, we take the pain of tabulating all the possible outcomes. We make a chart of that. And once the sample space is known to us, we say that, okay, this is the sample space with this size. And according to our requirement that we want at least 7 heads, we try to find out those favorable cases which satisfy my requirement. Okay, and we have said that by classical definition of probability, a favorable number of case by total number of case, the chance. So this is what we do, but we have to take the pain of writing all the elements of the sample space. Okay, and the persons who can do it in their mind, they will be able to do it quickly than us. But once you know a distribution, then once you know the characteristics of the distribution, once you know the parameters of the distribution, and if you can identify that this situation, it is a situation I'm giving you, this situation is actually satisfying the properties of that distribution, then it becomes easy for us to calculate the probability. Now, 10 coins are thrown simultaneously. We learned binomial distribution and Poisson distribution. So let us first check whether this falls under the category of binomial or Poisson. Okay, so we will first check it, and I am writing this on the board, but I'm suggesting not to do it when you will be solving the problems, because I am doing it just to make you understand the meaning of these two distributions. Okay, how to identify. Now, that is number of times repeated, number of experiments, and small probability of success in one experiment. Okay, this is the requirement of binomial. These are the parameters of binomial variate, and success should be well defined. Okay, success will be well defined if your sample space is well defined. And not only this, trials must be independent. Trials are independent. And with respect to the Poisson distribution's characteristic, the parameter, as you know, it's lambda, which is the product of the binomial distribution's parameter, small n and p. Maybe this number is a significant number. I mean, in the sense that if we can identify small n and small p, then we can also identify lambda. But at the same time, we have to keep in mind that whether this n, the number of experiment, is tending towards infinity and probability is tending towards 0 or not. These are the two extra conditions and the most vital conditions under which binomial distribution tends to follow Poisson distribution. But immediately I can say that this is not happening because n is number of experiment is finite here, finite, and therefore only 10 coins have been thrown. So therefore this particular criteria is not being satisfied. So therefore we shall not be using this Poisson distribution in this particular problem. So only we are left with binomial. Now throwing 10 coins simultaneously is equivalent to throwing a single coin 10 times. I think that you know this fact. 10 people are throwing a coin simultaneously, their respective coins simultaneously. It is equivalent to throwing a single coin 10 times. And each of these throwing are independent. Each of these are independent. It is pretty obvious. Okay. So from there, I can say that number of experiment being repeated here is 10. Now, we are interested in the fact of finding heads. That is important to us. Okay, so getting head is our success. The success is well defined. Okay, and probability of success is success in one experiment. So that means if we consider only one throw, then probability of getting head is equal to half, or you can say probability of success is half. Here we are assuming, since nothing is given, nothing is mentioned over here, only it is said that 10 coins are being thrown. If nothing is mentioned, we will consider the coin to be unbiased. Remember this. This is a vital point. If nothing is mentioned specifically in the question, we shall assume without any loss of generality that the coin is unbiased. And we know that this PS can be written by can be denoted by small p also. So immediately the probability of failure, which is nothing but the probability of getting tail, which is nothing but 1 minus p, is also equal to half. Okay, because getting success and failure are equally probable. So you see, from there I can say that this parameter n, which is 10, and this parameter p, which is half, these parameters are known to me. Once these parameters are known to me, we know the trials are independent, so we are able to apply the binomial probability law in this particular case. Okay, so I'm going to the next page. Now, if we consider capital X to be the random variable, which gives the count of head, which gives the count of heads, then small x heads are obtained will have the probability of x equal to small x which is ncx q to the power x q to the power n minus x. Sometimes ncx is also written in this manner. I think you know this. Okay, so ncx q to the power x q to the power n minus x, where x goes from 0 1 2 dot 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 up to n. 0 means no success. So in this way we have defined our random variable capital X. Why this particular random variable will have this probability? Because as it is clear from the question, that X follows binomial distribution. X follows binomial distribution. X follows binomial distribution with parameters small n and p, with parameters small n and p. X follows binomial distribution with parameters small n and p. Now we are interested in finding probability of at least 7 heads. We are interested in finding the probability of at least 7 heads. So the probability of getting at least 7 heads is equal to probability of X greater than or equal to 7. How many times the coin have been repeated? We know the coin has been repeated 10 times, and coin has been tossed 10 times, and therefore the possible discrete values of this probability are probability that X equal to 8, probability that X equal to 9, probability that X equal to 10. And as you know that the probability of these things are given by this probability law, so we can write it as 10 for a probability that X takes the value 8, that will be 10 10c8 half to the power 8 half to the power 10 minus 8. That is 1. 10c9 half to the power 9 half to the power 10 minus 9. 10c10 half to the power 10 half to the power 10 minus 10. Okay, and I'm writing here, and you can further simplify this. So this becomes 10c8 and half to the power, if I add the exponents, we will get half to the power 10 plus 10c9. If we add the exponent, we get half to the power 10. And lastly, also 10c10 means 1, so we'll get half to the power 10. And you can take half to the power 10 common, and that would be 10c8 plus 10c9 plus 1. Now you can further simplify this, or you can keep it as it is. Okay, I'm leaving this to. Oh, okay. One student, he Aratrik, thank you so much. I missed this point. Probability of X greater than or equal to 7. Yeah, thank you so much. Probability of X equal to 7. Since equality sign is there, so probability of X equal to 7 will also be there. So I missed this portion. So we can write it as one extra probability will be counted, half to the power 7, half to the power 10 minus 7, 10 minus 7 plus sign will you must give, and here one extra term will come. I'm writing here 10C7 half to the power 10 for this, and lastly just half to the power 10. So we'll get 10C7. So you can calculate this probability if you wish. You can further simplify this, and I'm leaving this for you. Okay, so I'm not going to calculate it further. I'm just showing you the way by which it is calculated. Now, in this particular problem, as the problem was given, what is the probability that only there is at least 7 heads? Suppose someone is asking you, what is find the probability of getting at most 7 heads. So that means you are supposed to, if I consider this part to be, number 1, the number 2 for the number 2 we don't have to calculate any further. So probability of getting at most 7 heads, that would be equal to probability of x less than or equal to 7. Okay, now at most 7, this means that, remember, this means that 7 or less than this. At most 7 means 7 or less than that. So probability of x less than or equal to 7 can be found by this complementary event probability, which is probability of A is equal to 1 minus probability of A complement. But here, remember, the equality symbol will not be there. So in this particular case, we will just write probability of x equal to 8 plus probability of x equal to 9 plus probability of x equal to 10, and so on. In this manner, you can calculate any probability as per the requirement. So it becomes so easy for us to calculate the binomial probability, but to calculate the probability if a system is identified properly. Okay, let me show you another problem. This problem is very important, and several times it came in the examination. So I'm putting a star over here. Okay, it is given that example 2. It is given that if x, okay, then show that E of x by n minus p whole square is equal to pq by n, and now this problem I'm going to do for you. Okay, don't think about this term. Whenever I'll explain what does this mean actually, but first of all, let me explain term by term. What does this mean? Let me try to explain this to you. Now, this means when a random variable x follows binomial distribution with parameters small p and q, small p and n, we write it in the way we say that x following binomial distribution with parameters small n and small p. So therefore, by this part, it has been told to you that the system is following binomial distribution. Expectation, you know. Now, what is given over here? Now, you see, if you have gone through my yesterday's video, so you will have come to know that for a binomial variate, for a binomial variate, expectation or mean expectation of x or mean of the binomial variate x is given by the formula NP, and variance of x or variance of the binomial variate is given by the formula NPQ. We know this. Okay, so now these two results are very important and we are going to use it over here. Now I am naming this as equation number 1 and this as equation number 2. If you are copying, I'll ask you to quickly copy or take a screenshot because I'll be moving to the next page sooner. Now from 1, we can divide both the side by small n, and if we do so, we will get E of x by n equals to P. Okay, but we know that if C is a constant, expectation of Cx is equal to C into expectation of x. Okay, we know this property. Therefore, you can put 1 by n here. 1 by n is the constant, so you can put 1 by n inside the expectation sign, and therefore it becomes expectation of x by n, and we can say that this is equal to expectation of x by n. This becomes your small p. Okay, so I can put a equation number star over here. So expectation of x by n is equal to small p. Now we are going to prove this first of all. Okay, I'm going to the next page. Left hand side, we are supposed to find expectation of x by n minus p whole square. Okay, and you know that small p is given by this term, expectation of x by small n. So in place of small p, we can put expectation of x by small n whole square. Now, if you can recall one of my earlier classes, then probably you have identified that, or you can recall that I told you when x is any random variable, then variance of x actually has got two different formula. One formula for variance of x is ex square minus ex whole square. That is one of the formulae. And another formula for variance is e of x minus ex whole square. That is another formula. Now try to correlate this formula with this that I have got. Now, if I try to correlate these three things together, we'll find that we can easily write this as variance of x by n. And if you can recall, this is point number 1. This is number 1. And if you can recall that I also wrote the property of variance as variance of Cx is equal to C squared variance of x, whereas expectation of Cx is equal to C into expectation of x. Try to find out the difference where C is a constant. Okay, then in this particular case, if I treat 1 by n to be constant, we can take it outside, and if we take it outside, we'll get 1 by n squared into Vx. But we know that Vx is NPQ from equation 2. Okay, yeah, here you can write that this line has been obtained. This line has been obtained from star, and from equation 2, now we can write that this is equal to 1 by n squared. Variance of x is npq. Now n cancel one n from the denominator and we get pq by n, which is your right hand side, and thus we have proved one of our statements. What is COV? Now COV stands for covariance. Covariance is actually the mutual deviation of two variables from their respective means. So in covariance, we need two different variables. So generally, I shall explain covariance in detail when we'll study correlation. Covariance of x comma y, if x and y are two different random variables, is given by the formula expectation of x minus ex and y minus ey. This is the formula. Try to remember this. Very important formula. Covariance of xy is equal to E of x minus ex, y minus ey. This implies, for a special case, if the two variables are actually same, so covariance of x and x will be equal to E of x minus ex and x minus ex, which can be easily written as E of x minus ex whole square, and that is nothing but equal to V of x. Okay, so I'm asking all of you to remember this formula. Okay, so now what am I supposed to find? I am supposed to find this quantity. Okay, so let us start. Left hand side, covariance COV x by n minus n minus x by n. Sorry, not minus, sorry, comma, n minus x by n. That can be written using the formula expectation of x by n minus E of x by n. That is one. And another variable, this is your, if you call this as your x and this as your y, then you can correlate the thing, and that can be written as n minus x by n minus expectation of n minus x by n. Okay, now let us try to keep the first part as it is. Let us not change anything over here. We can do a bit of calculation simplification in this case. So we can write it as n minus x by n, and you know this can be written as this can further be simplified as I can take 1 by n common outside, and inside we can write this. Okay, and if I want to further simplify, no, just a minute, let us not do this thing. I can do what you can say, that I can divide the numerator by the denominator like this. That would be more appropriate. Okay, and we are keeping this as it is. Here also I'm writing 1 minus x by n, and that is expectation of 1 minus x by n. Now you know that expectation of x plus y is equal to, or expectation of x plus minus y is expectation of x plus minus expectation of y, and expectation of constant is a constant quantity. So we can apply these results, or expectation of x plus c. This is nothing but expectation of x plus c. These results can be easily proved. Okay, so for both continuous and discrete cases. So we are going to use the result C over here. So we get expectation of x by n minus expectation of x by n, 1 minus x by n, and this, by using this result here, we can write plus minus. Okay, expectation of 1, okay, and minus expectation of minus x by n. Further simplify it, expectation of x by n, e of x by n, and you know expectation of 1 is, expectation of constant is constant, so it will be minus 1. And if you consider this minus to be a constant, minus 1, you can take it outside, it will become plus. So we get expectation of x by n. Ultimately, what do we get? This one will cancel that one. And what do we get? We'll get expectation of x minus n, e of x minus n, x by n, into minus x by n plus expectation of x by n. And you can take this minus outside. So we are getting ultimately expectation of x by n, e of x by n. And this is x by n minus expectation of x by n. Okay, now you see, if we consider the random variable to be x by n, I have already told you that if the two random variables are same, covariance of xy is becoming this. Okay, it becomes actually the variance of x. We have already proved it. I have already shown it. So by this rule, we can write that this is minus of v of x by n. Now I'm writing over here just to save the space. Now, therefore, covariance of x by n minus x by n is equal to minus v of x by n. And if we again take the constant 1 by n outside, we can write it as 1 by n squared vx. But you know that vx is npq because it is a binomial variate. So we can put it over here, npq, and lastly we get minus pq by n, which is the right hand side, which proves the desired result. I shall ask all of you to take a screenshot of these 3 pages, 4 pages, quickly, because we are not, the time is too short. This is page number 1. Take a screenshot of that. Take a screenshot, and one of you just raise your hand so that I can move on to the next page. Okay, so next page, this is page number 2. Take a screenshot. Okay, and that is page number 3. And lastly, we have page number 4. Page number 4. Oh, 5 pages are there. And that is page number 5. Okay, so in this session, I have told you many more examples of binomial variance, binomial distributions are there. Many more examples are there. In a single class, I could only do one or two, but it is up to you to solve other problems of binomial variate. Okay, so try to Try to do it by yourself. Try to find problems on binomial variate and try to do it by yourself. In the next session, I shall discuss the Poisson variate. Okay, so let's meet in the next session. I'm stopping the recording.